There are 120 of these, and not all of them are facts. Some are things nobody has worked out yet. None of them are the ones from school. They are the ones that took somebody a working life to settle, or that everybody had comfortably wrong for a century before anyone thought to check, or that are still sitting there unexplained. They don't build on each other, so each one stands on its own, and there's nothing you need to keep hold of, and nothing at the end you have to be awake for. If you drift off somewhere around Jupiter, that is more or less the idea. We'll start at the Sun and work outward, and we won't be in any hurry about it. The light landing on your window this afternoon is older than your species, and the delay has nothing to do with the distance. It is the getting out that takes the time. Energy down there begins as gamma rays, in a core sitting at close to 15.7 million Kelvin, and a gamma ray born in that core does not really travel outward at all. It goes a few millimeters and something absorbs it, and then it is thrown out again in whatever direction happens next, at slightly less energy, and absorbed again, and thrown out again, and the whole slow business repeats in a place so crowded that a straight line is not available to anything. So it staggers. Estimates of how long a single packet of that energy takes to reach the surface run from 10,000 years at the low end to 170,000 at the high end, which is a very wide bracket for something we can see from here. Neutrinos, which hardly interact with matter at all, cross the same distance in 2.3 seconds. Something up there is heating the sun's atmosphere, and after decades of work, nobody has established what. It is the sort of problem that should have been settled in the 1950s, and it is still open. Walk away from a fire and you get colder. The sun does the opposite of that in plain view, and has been doing it for as long as anyone has had an instrument pointed at it. The photosphere, which is the visible surface, sits at roughly 6,000 Kelvin, while above it, the corona runs to 1 or 2 million, and in the hottest patches, somewhere between 8 and 20 million. Heat does not flow from cold to hot. There are two candidates, and in the first, turbulence underneath the surface throws waves upward, and they give up their energy into the thin gas above as they die. In the second, the churning surface twists magnetic field lines past the point where they will hold, and they snap and reconnect, releasing that energy as flares and as a great many much smaller events called nanoflares. The trouble with the waves is that nearly every kind of wave dissipates or bends away before it ever gets up there, which is a serious problem for the first explanation. So the work has quietly moved across to the flares. For 37 years, the sun appeared to be missing 2/3 of something, and the people counting could not tell whether the fault was in the sun or in their instruments. It turned out to be neither. In the 1960s, people built detectors deep underground to count the neutrinos arriving from the sun. The theory said how many there should be, and the detectors found about 1/3 of that, which is not the sort of gap you can put down to instrument error, and it sat there with a name, the solar neutrino problem, for decades. Neutrino oscillation was confirmed in 2001, and it resolved the whole thing. The sun had been emitting exactly the predicted number of electron neutrinos the entire time. Neutrinos, though, change flavor as they travel. So by the time they arrived, 2 out of 3 had turned into a kind those particular detectors were blind to. Nothing had ever gone missing. The instruments had been counting the wrong thing. There is one place inside the sun cold enough for water to exist, which sounds like it should not be true of a star. It is true, and the layer is very thin. About 500 kilometers above the visible surface, there is a temperature minimum region sitting at roughly 4,100 Kelvin, which is still hot enough to vaporize anything you have ever held and cool enough for chemistry. Simple molecules can hold themselves together there, and the two that manage it are carbon monoxide and water, which is not something most people would expect to find anywhere near a star. Water molecules in the atmosphere of a star, they have nowhere to go either. Below them, the photosphere is hotter, and above them, the temperature starts its long climb toward the corona. The layer is therefore a thin band of relative cold pressed between two hotter things, and it is the only part of the entire sun where a molecule survives at all. Everywhere else, the atoms are pulled apart. The middle of the sun appears to be turning at a different speed to the rest of it, and there is nothing solid in there for one part to grip against another. Nobody has fully explained how that arrangement holds. The sun does not rotate as a single object. Its surface goes round at different speeds at different latitudes, the equator quicker than the poles. That much has been understood for a long time. It is the engine behind the magnetic cycle we'll get to shortly. Analysis of data from the ESA Hubble mission points at something further in than that. The core appears to be turning faster than the radiative zone wrapped around it, which is worth sitting with for a second. There's no surface anywhere in there, no boundary you could put a hand on, nothing but plasma getting denser as you go until it reaches 150 grams per cubic centimeter at the center. That is 150 times the density of water. That innermost region turns at its own rate, sliding against the layer above it. Almost none of the sun is actually burning, and the part that turns out to be surprisingly small. Everything else is just in the way. Fusion happens only in the core. It runs out to about 20 or 25% of the radius. 99% of the sun's power comes from the innermost 24%, and past 30%, almost none of it is happening at all. Everything outside that is insulation, layer on layer of plasma, whose entire job is moving heat outward from a small hot center to a surface where it can finally get away, which is why it takes those tens of thousands of years to escape. The reaction is a chain that fuses protons together, and it happens about 9, followed by 37 zeros times every second. A number I am not sure anybody can really picture. A second sequence, the CNO cycle, supplies 0.8%, and that share grows as the sun ages. There is a layer of the sun that light takes 1,000,000 years to cross, and it is not especially thick. The problem is what is in the way. The radiative zone is the thickest layer of the sun, starting just above the core at about a quarter of the way out and continuing to about 70% of the radius. It is named for how energy moves through it. Photons scatter from the dense gas so often that crossing takes them roughly 1,000,000 years. The temperature falls from about 7 million Kelvin to 2 million across that span, and the density drops 100-fold at the same time, from 20,000 kilograms per cubic meter down to 200. That gradient is the reason the zone behaves as it does. It is too shallow to drive convection, so the heat cannot simply rise. It has to be passed along, photon by photon, for 1,000,000 years. The sun has never been yellow, and the color you have been picturing your whole life belongs to the air rather than the star. Cultures do not even agree on which wrong color it is. Seen from space or from the ground when it is more or less overhead, its color sits near the middle of the color space, which is to say it is white. Its output per wavelength actually peaks in the green. The yellow belongs to our own atmosphere. Scattering takes the shorter wavelength out of the direct beam, and what is left arrives shifted toward yellow, then orange, then red as the sun goes down. Some cultures picture the sun yellow and some picture it red, and the reasons for that split are still debated, and occasionally it is green. Because just after sunset light from below the horizon bends through a temperature inversion and there is a green flash. A second or two of it, from a star that was white the whole time. Sunspots do not appear where you would expect, and they migrate across the face of the sun in a pattern regular enough to carry somebody's name. It took 2 centuries of watching to notice. At solar minimum, there may be very few and sometimes none at all, and the ones that do appear form at high latitudes, well away from the equator. And then as the cycle builds toward maximum, the new spots come in progressively closer to the equator. That drift is Sporer's law. A sunspot is not a hole. It is a place where the magnetic field has bunched up enough to get in the way of convection, so heat cannot rise into that patch as freely as it does everywhere else. That leaves it a little cooler than its surroundings, and looking dark only by comparison with what is next to it, which is the whole of the effect. The big ones run tens of thousands of kilometers across, and the 11-year cycle everyone has heard of is only half of the real one, because the magnetic polarity of the pairs flips over each time round. The actual period is 22 years. People were recording sunspots 2,000 years before anyone had a lens to look through, and for most of that time, nobody in Europe knew the records existed. When the argument finally started, it was not about whether the spots were real. Astronomers of the Han Dynasty, between 202 BC and AD 220, recorded observations of spots on the sun. Those records were kept up for centuries afterwards, and Averroes described them again in the 12th century. They were watching real magnetic structures on the surface of a star with no instrument at all, and no framework that could account for any of it. When the telescope did arrive, early in the 17th century, the question was where the spots were. Galileo held that they sat on the sun's surface rather than being small objects passing between the sun and us, and he was right about that. The observation had already been sitting in the written record in another hemisphere for over 1,000 years. The sun probably needed a nearby star to explode before it could form at all, and the evidence for that is sitting inside meteorites. It is a strange sort of inheritance. The sun came together about 4.6 billion years ago out of part of a giant molecular cloud of mostly hydrogen and helium, a cloud which probably gave birth to a good many other stars at around the same time as it made ours. That age comes from models of stellar evolution and agrees with the oldest solar system material we can date, at 4.567 billion years. Then there is the awkward detail. Ancient meteorites carry traces of the daughter products of isotopes with very short lives, iron 6 rho among them, and those form only inside exploding stars. So one or more supernovae must have gone off near where the sun formed. The shock wave from a nearby explosion would have compressed the cloud and pushed certain regions into collapsing under their own weight. Something had to die first. Mercury and Venus already have a date with the sun, and the calculations have been done. What happens to Earth is genuinely unsettled, and it comes down to a number nobody has pinned down. In something like 5 billion years, the hydrogen fusion in the core stops, and with nothing holding the core up, it contracts, and the energy that comes out of that contraction makes the sun brighter rather than dimmer. Eventually, more than 1,000 times as bright as it is now. Then it swells. It becomes a subgiant for 1 billion years or so, and then a red giant. And as it goes, it reaches Mercury, and then Venus, and takes them both without much ceremony. Earth's orbit may widen at the start, as the sun sheds mass, perhaps out to 1.5 times where it sits now. Then tidal forces may pull it back in, to be swallowed 7.6 billion years from today. Though the honest position is that nobody knows, because the sun's total mass loss is not pinned down well enough to say either way. Earth might come through it. Mercury will not. The planet closest to the sun is holding water ice, and has probably been sitting there for billions of years. The trick is that some of it has never once been in sunlight. Surface temperatures on Mercury run from 100 Kelvin up to 700, which is minus 173 degrees Celsius at the bottom and 427 at the top, and the sunlight falling on it is between 4.6 and 10.6 times as intense as what reaches Earth. Then there are the poles. The floors of the deepest craters there are never exposed to direct sunlight at all, because Mercury has almost no axial tilt to swing them into the light, and temperatures on those floors stay below 102 Kelvin. That makes a cold trap, and water arriving by comet or micrometeorite gets caught there and simply stays, because there is nothing to warm it and nowhere for it to go. Radar sees it plainly, because water ice is strongly reflective at those wavelengths, and the deposits show up exactly where the permanent shadows are and nowhere else on the whole planet. Ice on the hottest surface we know of. For most of a century, everybody was confident Mercury kept one face permanently toward the sun, and the confidence was entirely misplaced. It took a radar telescope to break it. The assumption was reasonable because the moon does exactly that with Earth. One face locked toward us, and a small planet sitting that close to a very large star ought on the face of it to behave the same way. Radar observations in 1965 showed something stranger. Mercury turns 3 times for every 2 orbits it completes, which is a spin-orbit resonance nobody had predicted, and it is stable rather than transitional. What holds it there is the shape of the orbit. Mercury has the most eccentric orbit of any planet in the solar system, so the strength of the solar tide varies enormously around one circuit, and at closest approach, where the tide is strongest, the sun is very nearly stationary in Mercury's sky. A circular orbit could not do that at all, because the variance in the tidal force is the thing doing the locking. One consequence is that a single day on Mercury, sunrise to sunrise, lasts about 176 Earth days, 2 of its years. In 1859, the orbit of Mercury refused to match Newtonian mechanics, and the explanation that everyone reached for was an undiscovered planet. It was named, searched for at length, and never found, because it does not exist. Urbain Le Verrier reported that the slow precession of Mercury's orbit could not be accounted for by Newton's laws and the pull of the known planets. He suggested there might be another planet closer to the Sun than Mercury, or perhaps a scattering of smaller bodies, and the proposal was taken seriously for very good reasons. Le Verrier had form. Neptune had been found on exactly that logic, predicted from the way it tugged at the orbit of Uranus, and the search had worked. So astronomers spent decades looking for a planet they had already named Vulcan, and some of them reported seeing it. The observed precession is 574 arcseconds per century, and Newtonian mechanics accounts for all but about 43 of them. That remainder is what general relativity explains, and explaining it was one of the first real tests the theory passed. The missing planet was a missing theory. Mercury is smaller now than it used to be, and the wrinkles left by the shrinking are all over its surface. Some of them are recent enough to be considered ongoing. The surface is crossed by compression folds, called roops, and they exist on the Moon, but are far more prominent here. As the interior cooled, it contracted, and the crust had to deform to fit a smaller inside. Some of these scarps reach 1,000 kilometers in length and 3 kilometers in height. Mapping them out across the surface suggests the radius of the whole planet has shrunk by somewhere between 1 and 7 kilometers since the crust first hardened. Most of that happened long ago, and the major thrust systems went quiet about 3.6 billion years back. Then there are the small ones. Scarps only tens of meters high and a few kilometers long, which appear to be less than 50 million years old, which in geological terms is very close to the present. The planet is still contracting. Mercury has a global magnetic field, and when the first spacecraft found it, the people who study planets were genuinely surprised. Its rotation is far too slow for that to work. The field is real, and it is dipolar, aligned within 10 degrees of the spin axis, much as Earth's is. It runs at about 1% of Earth's strength, which sounds negligible until you consider what is producing it. A field like that normally comes from a dynamo, which needs a liquid metallic core in motion. Mercury rotates once every 59 days. That is nowhere near fast enough to stir a core the conventional way. So the likely answer involves the same eccentric orbit that locked the spin. The tidal heating from swinging so close to the Sun and back keeps part of the core molten, and a molten core can circulate. Mariner 10 detected it on the first close pass in 1974, to the great surprise of planetary geologists. Mercury has a global magnetic field, and when the first spacecraft found it, the people who study planets were genuinely surprised. Its rotation is far too slow for that to work. The field is real, and it is dipolar, aligned within 10 degrees of the spin axis, much as Earth's is. It runs at about 1% of Earth's strength, which sounds negligible until you consider what is producing it. A field like that normally comes from a dynamo, which needs a liquid metallic core in motion. Mercury rotates once every 59 days. That is nowhere near fast enough to stir a core the conventional way. So the likely answer involves the same eccentric orbit that locked the spin. The tidal heating from swinging so close to the Sun and back keeps part of the core molten, and a molten core can circulate. Mariner 10 detected it on the first close pass in 1974, to the great surprise of planetary geologists. Mercury is the most difficult of the 8 planets to visit, and it is not because of the distance. Getting there is easy enough. Arriving is the problem. Falling toward the Sun is downhill all the way, and everything that falls picks up speed. A spacecraft dropping 91 million kilometers into the Sun's gravitational well converts all of that height into velocity and arrives moving far too fast to stop. Mercury orbits at 47.4 kilometers per second. Earth manages 29.8. To enter orbit, rather than sail past, a spacecraft has to shed an enormous amount of speed. On most planets, you could use the atmosphere to brake. Mercury has almost none, so a row braking is ruled out, and every bit of that slowing has to come from rocket engines carrying their own fuel. Which is why Mercury needs a higher change in velocity than any other planetary destination. More than Mars, more than the outer planets. Mercury is the second densest planet anywhere in the solar system, and it is also the smallest, which is a combination that takes some explaining. The answer is that most of it is metal. Its density is 5.43 grams per cubic centimeter, only just below Earth's 5.52, which on the face of it looks unremarkable until you start accounting for the effect of compression. Earth is large, so its own gravity squeezes its interior and inflates the figure. Mercury is small and barely compressed at all. Take the squeezing out of both, and Mercury's materials come out at 5.3 against Earth's 4.4, which means that the stuff Mercury is actually made of is genuinely denser than the stuff Earth is made of, rather than merely appearing that way. For that to be true, the core has to be enormous and rich in iron. Underneath a thin silicate crust and mantle, there is a solid metallic outer core layer, then a liquid core layer, then a solid inner core, a ball of iron with a rind of rock. There is a crater on Mercury with a set of troughs radiating out of it like the legs of an insect, and nothing else in the solar system looks quite like it. Its informal name stuck for obvious reasons. Apollodorus sits inside the Caloris Basin, and out of it run a series of radiating troughs extending away from the impact site. But the formal explanation is not settled. The troughs may be fractures that were already there when the impact happened, or the impact itself may have cracked the basin floor, and the ordering is hard to establish from images alone. The basin around it is worth a moment to. Caloris Planitia is 1,550 kilometers across, which on a planet 4,880 kilometers wide is about a third of the entire diameter. Everybody calls it the spider, and the formal name is used mainly in papers. The oldest surviving record of Mercury is roughly 3,400 years old, and whoever wrote it had already noticed the thing that makes the planet difficult. They called it the jumping planet. The observations come from the MUL Apen tablets, most likely made by an Assyrian astronomer around the 14th century BC, and the cuneiform name transcribes as the jumping planet, which is a fair description of something that never stays where you last saw it. Babylonian records run back to the first millennium BC, where the planet is Nabu, after the messenger of the gods. The Greeks took longer over one detail. They had two objects, an evening star and a morning star, and it was about 350 BC before they established the two were the same thing. In ancient China, it was the hour star, associated with north and with water. Modern Chinese, Korean, Japanese, and Vietnamese still call it the water star. Everybody who watched the sky carefully found it, and everybody found it annoying. The most famous telescope ever built has never taken a picture of Mercury, and it never will. The instrument is not incapable. It is forbidden. Mercury sits so close to the Sun that pointing anything at it means pointing near the Sun, and for the Hubble Space Telescope, that is an operational prohibition rather than a technical limit. The safety procedures exist because sunlight that intense would destroy the instruments. Telescopes on the ground can see it, but not well. What they show is a partial illuminated disk with very little detail on it, because Mercury is only ever visible in a brief window during morning or evening twilight, low down through the thickest part of our atmosphere. Its apparent magnitude swings more than any other planet's, from brighter than Sirius to below the limit of naked eye visibility. The nearest planet to the Sun is one of the hardest to look at. The 0 point for measuring longitude on Mercury was chosen badly, and the reason is that when the first spacecraft arrived, the correct spot was in the dark. So they picked a small crater instead. The convention puts 0 longitude at one of the 2 hottest points on the surface, which are determined by the resonance between spin and orbit. When Mariner 10 came past, that meridian was in darkness. There was no way to select a surface feature to fix its exact position because nobody could see any. So a small crater further west was used. It is called Homco, and its center defines the 20 degrees west meridian, which means every longitude on Mercury is measured from a crater chosen because the real reference point was unlit. Hunkal means 20 in Maya, which is at least a tidy sort of accident. One planet passing in front of another has been witnessed exactly once from Earth, and the observation is nearly 300 years old. The next opportunity is more than a century away. Mercury and Venus pass in front of one another every few centuries, seen from here, and the event of May 28, 1737 is the only one anybody has recorded. John Bevis saw it from the Royal Greenwich Observatory, and the next occultation of Mercury by Venus falls on December 3, 2133. Transits across the Sun are more frequent, but still rare, and Ptolemy had wondered about them in the 2nd century, suggesting either that the planets were simply too small to see against the face of the Sun, or that the alignments came round too infrequently for anyone to catch one. He was right about the second part. Pierre Gassendi made the first telescopic observation of a transit in 1631, working from a prediction by Kepler. Nobody alive today will see what Bevis saw. For nearly 400 years, observers have reported a faint glow on the night side of Venus, and nobody has ever confirmed it exists. It may not be there at all. The first claimed sighting of what came to be called the Ashen Light was made in 1643, and since then, it has been reported again and again by careful observers using good instruments, almost always when Venus is a crescent in the evening sky, with its night side turned toward us. The trouble is that nobody has reliably confirmed it. It has never been captured in a way that settles the question. Two explanations compete. Either something is genuinely glowing up there, perhaps electrical activity in that enormous atmosphere, or the whole thing is an illusion produced inside the eye by staring at a very bright crescent shape against a dark field. So the oldest open question about Venus may turn out to be a question about human vision rather than about the planet. Venus takes longer to turn around once than it takes to go around the Sun, and it turns the wrong way while doing it. Nobody has established why. A single rotation takes 243 Earth days. A full orbit takes 224.7, so the day is longer than the year, which is a state of affairs that no other planet in the solar system manages, and it means the ordinary relationship between spinning and orbiting simply does not apply there. The rotation is also retrograde. Venus turns clockwise on its axis while orbiting the Sun anti-clockwise, which is backwards compared with almost everything else in the system. The leading explanations involve a colossal early impact, or tidal forces acting on that thick atmosphere over billions of years, or some combination of both, and none of them is settled. One consequence is worth holding on to. Because the spin and the orbit nearly cancel, the interval from one sunrise to the next on Venus is about 117 Earth days. The path Venus traces against our sky draws a 5-pointed star, and it takes 8 years to complete one. Ancient astronomers noticed the pattern long before anyone could explain it. Earth and Venus sit in a near resonance of 13 to 8, meaning Earth completes 8 orbits for every 13 that Venus manages, and the near fit, rather than the exact fit, is what makes the geometry so striking. They come closest, at inferior conjunction, every 584 days on average. Plot those closest approaches from Earth over 5 of those cycles, and each one lands 144 degrees round from the last. 5 points, 144 degrees apart, which is a pentagram drawn by 2 planets that have never touched. It is sometimes called the petals of Venus, and the resonance is not perfect, so the figure drifts slowly rather than closing exactly. Venus also comes nearer to Earth at those moments than any other planet ever does, at an average of 41 million kilometers. The air at the surface of Venus is not really air, and it is not quite liquid either. It sits in a state that has no everyday equivalent, and standing in it would be more like being submerged. The atmosphere is 96.5% carbon dioxide, with most of the remainder nitrogen, and the pressure at the surface is 92 times what we have at sea level, which is roughly what a diver would feel about a kilometer down in our own ocean. At that pressure and 737 Kelvin, both main constituents are above their critical points, so the lowest layer of the atmosphere becomes a supercritical fluid rather than a gas. The density is 65 kilograms per cubic meter. That is 6.5% the density of water and about 50 times as dense as the air you are breathing. So a Venera lander did not descend through an atmosphere so much as sink into one. And the greenhouse effect this produces is the strongest in the solar system. Venus is hotter than the planet next to the Sun, despite being nearly twice as far away. The difference is not distance. It is what is holding the heat in. Surface temperature on Venus is at least 735 Kelvin, which is 462 degrees Celsius. It is very nearly the same everywhere. that holds at the poles, at the equator, on the day side and on the night side. And even after 117 Earth days of darkness, the night side barely cools at all. Mercury reaches about 700 Kelvin at its hottest point and drops to 110 on its dark side, a swing of nearly 600 degrees, because it has almost no atmosphere to move heat around or hold it. Venus has 92 atmospheres of carbon dioxide doing exactly that. The whole planet is held at roughly one temperature by the thickest greenhouse in the solar system, which makes it the hottest place with a solid surface anywhere we have looked. The entire surface of Venus appears to have been replaced at once, somewhere between 300 and 600 million years ago, and the craters are how we know. Almost all of them are pristine. There are nearly 1,000 impact craters on Venus, spread evenly across the whole planet. On the Moon, craters get worn down by later impacts, and on Earth, they are eroded by wind and rain, so a surface of any real age shows craters in every state of decay. On Venus, about 85% of them are in pristine condition. That combination, a moderate number of craters all in similar condition, points to a global resurfacing event followed by a decline in volcanism. And the crust we see now is only 300 to 600 million years old across the entire planet. Earth deals with its interior heat by moving crust around, recycling the ocean floor at subduction zones. Venus cannot do that. So the suggestion is that the heat builds until the crust fails everywhere at once. Venus has more volcanoes on it than any other body in the solar system by a very large margin, and it is not because it is more volcanically active than Earth. It is because nothing has cleaned them up. More than 85,000 volcanoes have been identified and mapped, and 167 of them are over 100 kilometers across, which is a size Earth manages exactly once in the Big Island of Hawaii. The reason is not extra activity, it is age and preservation. Earth's ocean crust is continually recycled at plate boundaries and averages only about 100 million years old, so most of the volcanoes that ever existed have been erased. The Venusian surface is 300 to 600 million years old, and there is no rain, no plate tectonics, and no ocean to remove anything. Everything that ever erupted is still sitting there. The sulfur dioxide in the upper atmosphere keeps varying, which suggests some of them are still going. Venus is nearly the same size as Earth, made of much the same material, and it has essentially no magnetic field of its own. That absence was a genuine surprise, and the explanation is stranger than the fact. Venera 4 found the field to be far weaker than Earth's in 1967. What little there is turns out to be induced, produced by the solar wind interacting with the ionosphere rather than generated in the interior, which means the planet has almost no protection from radiation. A dynamo needs three things, and they are a conducting liquid, rotation, and convection. The core is conductive, and although the rotation looks far too slow, simulations show it is actually adequate. So the missing ingredient is convection, and that is the interesting part, because it implies the core is not losing heat to the mantle fast enough to stir. The field is missing because the inside of Venus has stopped cooling properly. Two 18th century transits of Venus were used to work out the actual size of the solar system, and getting the measurement required, sending observers to opposite ends of the Earth. The pattern they occur in is nearly as strange as the reason it mattered. A transit happens when Venus crosses the face of the Sun, and because its orbit is tilted relative to ours, most conjunctions produce nothing at all. They only work when the alignment falls in early June or December. The result is a sequence of gaps: 8 years, then 105.5 years, then 8 years, then 121.5, repeating over a 243-year cycle. Jeremiah Horrocks made the first known observation in 1639 from a prediction by Kepler and the 1631 transit before it was the first ever successfully predicted. The value of a transit was that timing it from widely separated points on Earth gives you the distance to the Sun, and therefore the scale of everything else. The next pair falls in 2117 and 2125. Venus was the observation that broke the Earth-centered universe, and it did so in December 1610 because of something anyone with a small telescope can see. It shows phases like the Moon. Galileo watched it move from crescent to gibbous to full and back again, and reported what he had seen in his letters on sunspots in 1613. That sequence is the problem. In the Ptolemaic arrangement, where everything circles the Earth, Venus cannot show a full disk because the geometry never puts its illuminated face toward us when it is on the far side. Only a Venus orbiting the Sun produces the full run of phases. It also shows a half-lit face when it is furthest from the Sun in our sky, and a thin crescent when it is closest, which is the reverse of what a geocentric model requires. The phases are visible in a 4-inch telescope. Venus is bright enough to be seen in broad daylight with the naked eye, and most people go their whole lives without noticing. It has alarmed at least one city. At maximum, it reaches an apparent magnitude of -4.92, which makes it the brightest natural point of light in our sky after the Sun and the Moon, and it stays bright even at its faintest. Edmund Halley calculated its maximum brightness in 1716, in a year when its daytime appearance alarmed a good many Londoners who had no idea what they were looking at. Napoleon saw in daylight during a reception in Luxembourg. It was also observed in the daytime sky during Abraham Lincoln's inauguration in Washington on March 4, 1865. The reason people miss it is simply that they are not looking. It is there most days. The point on Earth's surface that sits furthest from the middle is not the summit of Everest, and it is not especially close to it either. The mountain that wins is in Ecuador. Because the Earth spins, it is not a sphere. It bulges at the equator, and the diameter there is 43 kilometers longer than the diameter measured pole to pole, which means everything sitting on the equator starts from a higher shelf. Everest reaches 8,848 meters above sea level, which is the greatest height anybody measures mountains by, and by that measure, nothing comes close. Measure outward from the middle of the planet instead, and the answer changes. The summit of the volcano Chimborazo in Ecuador sits 6,384.4 kilometers out from the middle, which is further than Everest manages. Both statements are true at once. Everest is the highest above the sea, and Chimborazo is the point on the surface nearest to space. Every day on Earth is very slightly longer than the one before it, and the effect is measurable with ordinary instruments. The Moon is taking the energy. The mean solar day is 86,400 seconds by definition, but the actual rotation no longer quite matches that, because tidal friction between the oceans and the Moon has been slowly breaking the planet for billions of years, and continues to do so now. Each individual day now runs between 0 and 2 milliseconds longer than the mean. That sounds negligible until you accumulate it. It is why leap seconds exist, and it's why the length of a day in the Devonian was closer to 22 hours than 24. There's also a second, stranger day. The rotation relative to the fixed stars takes 86,164.1 seconds, which is nearly 4 minutes shorter than the solar day, and that one is called the stellar day. Then there's a third. The sidereal day, measured against the moving equinox rather than the fixed stars, is shorter than the stellar day by about 8.4 milliseconds. Earth is losing its atmosphere into space continuously, and it has been for the entire history of the planet. The loss turns out to have been necessary. At the very outer edge, in the exosphere, thermal energy pushes some molecules to speeds above escape velocity, and those molecules simply leave. The process is slow and it never stops. Hydrogen goes fastest because it is the lightest thing up there and needs the least energy to reach escape velocity, so it leaks away at a greater rate than anything else. Here's the part that reframes it. That hydrogen loss is one reason the atmosphere shifted from a reducing state to an oxidizing one, because losing a reducing agent is thought to have been a necessary precondition for oxygen to accumulate at all. Photosynthesis supplied the oxygen. Leaking away the hydrogen is what let it stay. All of the water on Earth, every ocean and river and ice sheet, amounts to about 1 part in 4,400 of the planet's mass. Spread evenly, it would be a film rather than a depth. The oceans cover 361.8 million square kilometers at a mean depth of 3,682 meters, which gives a volume of roughly 1.3 billion cubic kilometers. And that sounds like a great deal until you compare it with the rock underneath. Flatten the crust to a perfectly smooth sphere and the resulting world ocean would be only 2.7 to 2.8 kilometers deep, everywhere. About 97.5% of it is salt water. Most of the remaining fresh water is not liquid at all, but locked up as ice. The blue we see from space is a coat of varnish on a stone. Earth's magnetic field has been losing strength throughout the whole period anybody has measured it, at roughly 6% per century, and the poles wander and occasionally swap ends. The behavior is chaotic rather than cyclical. The field is generated in the core by a dynamo, converting the kinetic energy of convection into magnetic energy, and it reaches the surface as an approximate dipole with its poles sitting near the geographic ones. At the magnetic equator, the surface strength is about 300 thousandths of a Tesla. But the convecting it is turbulent, so the poles drift, and every so often the whole field reverses polarity, which has happened many times in the geological record with no discernible regularity to it. The current decline needs one piece of context. Even after that 6% per century, the field is still stronger than its own long-term average. It has been weaker than this before. The moon appears almost exactly the same size in our sky as the sun does, and there is no reason for that to be true. It is a coincidence, and it is temporary. The moon has a diameter about a quarter of Earth's, which makes it the largest moon anywhere relative to the planet it orbits, though Charon beats it relative to Pluto. The coincidence is in the ratio of size to distance. The moon is small and near, the sun is enormous and far, and the two ratios happen to land within a few percent of each other, which is what makes a total solar eclipse possible at all, and it will not last. The moon is receding, so in the distant future, the disks will no longer match and total eclipses will stop happening. We are alive during the window when they line up. About half of the heat coming out of the Earth is not left over from its formation. It is being produced right now by the decay of 3 particular isotopes. The 2 sources are primordial heat, held over from when the planet assembled, and radiogenic heat, generated continuously as unstable atoms come apart in the mantle and crust. The 3 doing most of the work are potassium-40, uranium-238, and thorium-232. At the center, the temperature may reach 6000 degrees Celsius, with pressure around 360 gigapascals, which is roughly 52 million pounds per square inch. So the implication runs backwards in time. Isotopes with short half-lives have long since been used up. So the young Earth ran much hotter, and at about 3 billion years ago, it was producing twice the heat it does now. That meant faster convection, faster plate tectonics, and the production of igneous rocks such as komatiites that essentially no longer form anywhere. Earth has a deadline, and it is not the sun swelling into a red giant. The oceans go long before that, and the plants go first. Solar luminosity rises by about 10% over the next 1.1 billion years, and by 40% over the next 3.5 billion, which sounds gradual until you follow what the extra heat does to the carbon cycle. Rising surface temperature accelerates the inorganic carbon cycle, which may pull carbon dioxide down to levels too low for photosynthesis, possibly within 100 to 900 million years. No vegetation means no oxygen, and no oxygen means no animals of the kind now alive. Mean temperature may reach 100 degrees Celsius in about 1.5 billion years, and all the ocean water may evaporate and be lost to space somewhere between 1.6 and 3 billion years from now, possibly triggering a runaway greenhouse. The sun does not need to expand to finish this. It only needs to keep brightening. When the oceans first formed, the sun was only about 70% as bright as it is today, which should have left the whole planet frozen. It was not frozen, and the reason is still argued over. The atmosphere and oceans came from volcanic activity and outgassing, with water vapor condensing out, topped up by water and ice arriving on asteroids, protoplanets, and comets. There may have been enough water present from the very beginning, but the problem is the temperature. A sun at 70% brightness is not enough to keep liquid water liquid. The usual answer is greenhouse gases, present in far greater quantities then than now, holding in enough heat to keep the oceans from freezing over. By 3.5 billion years ago, the magnetic field was established, which stopped the solar wind from stripping the atmosphere away entirely. The oldest surviving pieces of Earth are not rocks. They are single crystals, small enough to sit on a pinhead, and they outlast everything formed around them. As the molten outer layer cooled, it formed the first solid crust, thought to be mafic in composition, and the first continental crust formed later by partial melting of that earlier crust. Almost none of it survives, because plate tectonics has recycled nearly the whole of the original surface. So what does survive is zircon. Zircon crystals of Hadean age have been found, dating from the first 500 million years of the planet's existence, preserved inside much younger rocks that formed around them long afterwards. The rock is young, and the crystal inside it is ancient. Seasons have nothing to do with how far Earth is from the Sun, which is the single most commonly held wrong belief about the planet. The whole effect comes from a tilt of 23.4 degrees. Earth's axis is tilted about 23.439 degrees relative to the plane of its orbit, and it points at the same place in the sky all year round, which means that as the planet goes around, first one hemisphere leans toward the sun and then the other. Northern summer happens when the Tropic of Cancer faces the sun, and southern summer when Capricorn does. Winter occurs in the opposite hemisphere at the same moment, which is the detail that disposes of the distance explanation entirely, because both hemispheres are the same distance from the sun on any given day. Above the Arctic Circle, the effect goes to its limit, and there is no daylight at all for part of the year. Life on Earth started far sooner after the planet cooled than anyone would reasonably expect, and then spent most of its history doing almost nothing visible. The pause is the strange part. Chemical reactions produced the first self-replicating molecules about 4 billion years ago, which on a planet that formed 4.54 billion years ago is very nearly straightaway in geological terms. 500 million years after that, the last common ancestor of everything now alive appeared. Then photosynthesis arrived and changed the atmosphere because the oxygen it released accumulated and eventually built an ozone layer in the upper atmosphere, which absorbed the ultraviolet that had been making the surface uninhabitable. Only then could anything colonize the land. Complex cells came from smaller cells, being incorporated inside larger ones, and true multicellular life came later still, as cells within colonies specialized. For most of the history of life on this planet, the story is microbes and nothing else. Half of Mars may be a single crater, and if that turns out to be right, it is the largest impact scar we know of. The evidence is that the two hemispheres do not match. The dichotomy is obvious once you know to look for it, because the northern half is flat plains smoothed by lava, while the southern half is heavily cratered highlands standing kilometers higher, and there is no gradual transition anywhere between them. One explanation is a collision. About 4 billion years ago, the northern hemisphere may have been struck by an object somewhere between 1/10 and 2/3 the size of our moon. If that happened, the resulting basin is 10,600 by 8,500 kilometers across, which is roughly the combined area of Europe, Asia, and Australia. That would surpass the South Pole Aitken Basin on our moon and everything else known. It is not confirmed. The candidate is simply too large to see as a crater from inside it. Olympus Mons is either the tallest mountain in the solar system or the second tallest, and which one depends on where you decide the bottom is. The mountain is too big to measure cleanly. The edifice is over 600 kilometers wide, which is about the size of France, and the difficulty is that a mountain that broad has complicated edges rather than a base. Measure the local relief from the foot of the cliffs on its northwestern margin up to the peak, and you get over 21 kilometers. A little more than twice Mauna Kea measured from the ocean floor. Measure instead from the plains of Amazonas Planitia, 1,000 kilometers away, and the total elevation change approaches 26 kilometers, which is about 3 times Everest. The slopes average only about 5 degrees. Standing on it, you would not know you were on a mountain at all. Mars has no global magnetic field now, but parts of its crust are still magnetized in alternating bands. On Earth, those bands mean one specific thing, and it is not something Mars is supposed to have had. The magnetized regions record alternating polarity, which implies that the dipole field reversed itself repeatedly while the rock was still forming, in exactly the way that Earth's field does to this day. The pattern is the striking part. Alternating bands of magnetized rock are what you find on Earth's ocean floors, and there they are produced by new crust forming at a spreading ridge and being carried away in both directions. A hypothesis published in 1999 and revisited in 2005 suggests the bands mean Mars had plate tectonics about 4 billion years ago, before the dynamo shut down and the field faded. A dead planet with the fingerprints of a living one. There are 7 holes in the side of a Martian volcano, and nobody knows how deep 6 of them go, because no light reaches the bottom. The people who found them named them after their families. The thermal emission imaging system aboard Mars Odyssey revealed 7 possible cave entrances on the flanks of Arsha Mons. They are collectively called the 7 Sisters. The openings measure between 100 and 252 meters across, and the estimates put them at least 73 to 96 meters deep, though those figures describe floors that nobody has actually managed to see from orbit. Only one is different. Denna has a visible floor, measured at 130 meters down. The interiors would be shielded from micrometeoroids, ultraviolet, solar flares, and high-energy particles, which is a short list of everything that makes the Martian surface uninhabitable. If anything is alive on Mars, it is somewhere like that. Mars is having its atmosphere removed by the Sun, and the process has been running for 4 billion years. We can watch the gas trailing away behind the planet. The planet lost its magnetosphere about 4 billion years ago, possibly through repeated asteroid strikes, and without that shield in place, the solar wind interacts directly with the ionosphere and pulls atoms away from the top of it, one at a time. Both Mars Global Surveyor and Mars Express have detected ionized particles streaming off behind Mars, and MAVEN was sent specifically to study the loss. What remains is very thin. Mean surface pressure is 600 pascals, which is about 6,000ths of what we have at sea level, and the densest air on the whole planet, at the bottom of Hellas Planitia, is equivalent to Earth's atmosphere 35 kilometers up. The lowest pressure is on top of Olympus Mons at 30 pascals. The southern hemisphere of Mars gets substantially hotter summers than the northern one by up to 30 degrees, and the reason is the shape of the orbit rather than anything about the ground. Mars has seasons like Earth, driven by axial tilt, but its orbit is far more eccentric than ours. But the timing is what matters. Mars reaches its closest approach to the Sun during southern summer, and its furthest point during southern winter. So the southern hemisphere gets its summer while receiving the most sunlight available, and its winter while receiving the least. That makes southern seasons more extreme and northern ones milder than the tilt alone would produce. Surface temperatures across the planet run from about minus 110 degrees Celsius at the coldest to as high as 35 in equatorial summer. Which is to say, Mars sometimes has pleasant afternoons. Mars carries 43,000 impact craters at least 5 kilometers across, and the largest one you can actually see could hold most of a continent. The count is only possible because nothing erases them. About 60% of the surface shows a record of impacts from the era known as the Late Heavy Bombardment, and much of the remaining surface is probably underlain by immense impact basins dating from that same violent period. Though the Late Heavy Bombardment itself is now disputed, more recent modeling questions whether the spike in impact happened at all. The largest exposed crater is Hellas, and it is deep enough that the atmosphere at its floor is the densest on the planet. Craters larger than 50 kilometers are named after dead scientists and writers. Smaller ones get the names of towns with populations under 100,000. The orbit of Mars is the reason we know that planets travel in ellipses, and Kepler needed 10 years and somebody else's observations to see it. A circle very nearly worked. He published the 10-year study in 1609 using measurements of the diurnal parallax of Mars made by Tycho Brahe, and Brahe's data was the most precise available anywhere in the world at the time. From it, Kepler deduced that Mars does not orbit the Sun in a circle, but in an ellipse, which broke an assumption that had held since antiquity. And he also noticed the speed changing. Mars moves faster when it is nearer the Sun, and slower when it is further away, which physicists would later explain as conservation of angular momentum. Mars was the right planet for this. Its orbit is eccentric enough that a circle visibly fails, and nearby enough for Brahe to measure precisely. Mars carries 43,000 impact craters at least 5 kilometers across, and the largest one you can actually see could hold most of a continent. The count is only possible because nothing erases them. About 60% of the surface shows a record of impacts from the era known as the Late Heavy Bombardment, and much of the remaining surface is probably underlain by immense impact basins dating from that same violent period. Though the Late Heavy Bombardment itself is now disputed, more recent modeling questions whether the spike in impacts happened at all. The largest exposed crater is Hellas, and it is deep enough that the atmosphere at its floor is the densest on the planet. Craters larger than 50 kilometers are named after dead scientists and writers. Smaller ones get the names of towns with populations under 100,000. The orbit of Mars is the reason we know that planets travel in ellipses, and Kepler needed 10 years and somebody else's observations to see it. A circle very nearly worked. He published the 10-year study in 1609 using measurements of the diurnal parallax of Mars made by Tycho Brahe, and Brahe's data was the most precise available anywhere in the world at the time. From it, Kepler deduced that Mars does not orbit the Sun in a circle, but in an ellipse, which broke an assumption that had held since antiquity, And he also noticed the speed changing. Mars moves faster when it is near the Sun and slower when it is further away, which physicists would later explain as conservation of angular momentum. Mars was the right planet for this. Its orbit is eccentric enough that a circle visibly fails, and nearby enough for Brahe to measure precisely. Mars has 2 moons, and nobody is sure where they came from, and one of them is falling. They are named after panic and terror. Phobos is about 22 kilometers across, and Deimos about 12, orbiting at 9,376 and 23,460 kilometers respectively, which makes them small enough and irregular enough in shape that the usual explanation is captured asteroids rather than anything that formed in place. Asaph Hall discovered both in 1877 and named them after the twins from Greek myth who went into battle alongside their father Ares. Phobos is the deity of panic and fear, Deimos of terror and dread. Mars was the Roman equivalent of Ares, and in modern Greek, the planet is still called Eris. Phobos orbits so close and so fast that from the surface it rises in the west and sets in the east, crossing the sky twice a Martian day. And it is spiraling inward. Eventually, it breaks up. There may be as much water inside Mars as there is inside Earth, and none of it is available. It is chemically bound into the rock. The chemical signature of water vapor on Mars was first unequivocally demonstrated in 1963 using spectroscopy from a telescope on the ground, long before anything landed there. So then the rovers found minerals that only form wet. Opportunity detected jarosite in 2004, which requires acidic water, and gypsum in 2011, and Spirit found concentrated silica deposits in 2007 that also indicate wet conditions. The upper mantle estimate is the surprising one. Hydroxyl ions held within Martian minerals amount to somewhere between 50 and 300 parts per million of water, which is equal to or greater than Earth's figure. Enough, if it could be released, to cover the entire planet. Egyptian astronomers had worked out that Mars sometimes moves backwards by 1534 BC, and the Babylonians knew its cycle to the year. To the Sumerians, it was a minor god who became a major one. The Sumerians called it Nergal, god of war and plague, and in Sumerian times he was a deity of little significance whose importance grew much later, with his main cult center eventually at Nineveh. Mesopotamian texts describe the planet as the star of judgment of the fate of the dead. By 1534 BC, the Egyptians were familiar with its retrograde motion, which is the apparent backwards drift that happens when Earth overtakes Mars on the inside. Babylonian astronomers under the Neo-Babylonian Empire kept systematic records and knew that Mars completes 37 synodic periods, or 42 circuits of the zodiac, every 79 years. For most of the 20th century, Mars was assumed to be inhabited, and then 2 landers settled the question in a way nobody had wanted. The answer held for decades. Mars 1 of the Soviet Union flew by in 1963, but lost contact on the way. Mariner 4 became the first spacecraft to transmit successfully from Mars, making its closest approach on July 15, 1965, and it returned the first images of another planet ever taken from deep space. And what those images showed was a cratered, cold, apparently dead world. Once spacecraft reached it in the 1960s and 1970s, many earlier ideas about Mars broke completely, and after the Viking life detection experiments returned their ambiguous results, the hypothesis of a dead planet was generally accepted. Mariner 4 also measured the radiation belt at about 1,000th of Earth's. The question has since been reopened. It was closed for 40 years. The largest storm on any planet has been shrinking throughout the entire period anybody has been measuring it carefully, and nobody has established why. It may also be much older than the records suggest. The Great Red Spot is an anticyclonic storm sitting 22 degrees south of Jupiter's equator, and it was first definitely observed in 1831, though there is a possible sighting as early as 1665, which would make it well over 350 years old if the two are the same storm. It rotates anticlockwise once every 6 days or so. It rises about 8 kilometers above the surrounding cloud tops. It is still larger than the whole of Earth, and it used to be considerably larger than that, which is the part that nobody has satisfactorily explained. Mathematical models suggest the storm is stable and should be a permanent feature, which sits awkwardly beside the fact that it has been measurably losing width for over a century. The source of the red color is also uncertain. Jupiter is the oldest planet in the solar system, and it formed absurdly fast, about 1 million years after the Sun itself. Earth took 50 million years longer to arrive. Models put its formation at or beyond the snow line, the distance from the young Sun where it was cold enough for water and other volatiles to condense into solids, and that abundance of solid material is what let it start so early. A solid core formed first and then gathered an atmosphere of gas around itself, which is the ordinary route to a giant planet. The mass had to accumulate before the solar nebula dispersed, which is an extremely narrow window, and once proto-Jupiter passed about 50 Earth masses, it opened a gap in that nebula. And after that, it reached its final mass in only 3,000 or 4,000 years. 3,000 or 4,000 years is how long it took to finish assembling the largest planet in the solar system. Everything else in the solar system formed in a system that already had Jupiter in it. Jupiter is the largest planet, and it also has the shortest day, which is a combination that has visibly deformed it. You can see the distortion in an amateur telescope. A full rotation takes slightly less than 10 hours, which is the fastest of any planet, and the centrifugal effect of spinning that quickly has pushed the equator outward until the equatorial radius is 7% longer than the polar one. Because Jupiter is not solid, different latitudes rotate at different speeds. The polar atmosphere takes about 5 minutes longer to come round than the equatorial atmosphere does. Astronomers therefore use 3 different rotation systems. System 1 for the equatorial band, System 2 for everything else, and System 3 for the interior as measured by radio emissions. So the planet does not really have one day at all, and depending which part of it you are watching, there are several. Jupiter takes about 200 times as many asteroid and comet impacts as Earth does, and for decades that was assumed to be protecting us. Simulations now suggest it may not be. The old picture was straightforward enough in that an enormous gravity well sitting just outside the inner solar system intercepts incoming comets, and the Earth is safer for having it there. Computer simulations in 2008 complicated that. Jupiter's gravity perturbs cometary orbits inward roughly as often as it captures or ejects them, so there may be no net reduction in the number of comets reaching the inner system at all. The argument is still live. Some hold that Jupiter draws comets toward Earth out of the Kuiper belt, and others that it shields us from the Oort cloud. In July 1994, the case for interception got its clearest demonstration when comet Shoemaker-Levy 9 broke apart and struck the planet in view of every telescope on Earth. Jupiter was expected to have either a solid core or no core at all, and the answer turned out to be neither. The Juno mission found something nobody had a category for. There were 2 competing pictures before this century, If Jupiter accreted as a solid body first, it should have a dense core, then metallic hydrogen out to about 80% of the radius, then molecular hydrogen above that. If it collapsed directly out of the gas disk, it should have no core at all, just steadily denser fluid hydrogen all the way down. Juno's data showed a diffuse core, which is neither solid nor absent, but heavy elements mixed gradually into the mantle across 30 to 50% of the planet's radius, totaling somewhere between 7 and 25 Earth masses. The boundary that both of the earlier pictures depended on turns out not to exist anywhere inside the planet. Jupiter's magnetic field is the strongest of any planet, and on the side facing away from the Sun, it stretches out almost as far as the orbit of Saturn. It is generated by liquid metal. The dipole moment is 4.17 Gauss, tilted about 10 degrees from the rotation axis, and surface strength varies from 2 Gauss up to 20, depending where you measure. What produces it is eddy currents in the fluid metallic hydrogen inside. That is, hydrogen compressed hard enough to conduct electricity, like a metal. The scale of it is the striking part, because a bow shock forms about 75 Jupiter radii out where the field first meets the solar wind. And on the downwind side, the magnetosphere is drawn into a tail reaching nearly to Saturn. All 4 of the Galilean moons orbit inside that field, which means they are permanently immersed in it. Jupiter has been broadcasting radio bursts since long before anyone had equipment to hear them, and one of its own moons is partly responsible for switching them on. The discovery was an accident. Bernard Burke and Kenneth Franklin found in 1955 that Jupiter emits bursts at 22.2 megahertz, and because the period of the bursts matched the planet's rotation, they were able to use them to pin down the rotation rate more precisely than optical observation had managed. The bursts come in 2 distinct lengths, the long ones lasting up to several seconds, and the short ones lasting less than 1/100th of a second. The decamtric bursts vary with rotation, and are influenced by Io moving through the magnetic field. A moon is modulating the signal. Frank Drake and Hein Havetum found the desymmetric emission in 1959. Galileo discovered Jupiter's 4 large moons and does not have the credit for naming a single one of them. Someone discovered them a day later and won that argument. He found them in 1610, and it is thought to be the first telescopic observation of moons other than our own, which mattered enormously because 4 objects visibly orbiting something other than Earth was direct evidence against an Earth-centered cosmos. Simon Marius found them independently 1 day afterwards, and did not publish until 1614. But Marius's names are the ones that stuck: Io, Europa, Ganymede, and Callisto. Galileo's own support for the Copernican model, strengthened by exactly this observation, led to his trial and condemnation by the Inquisition. There is a smaller footnote too. In autumn 1639, the Neapolitan optician Francesco Fontana discovered the atmospheric bands while testing a telescope he had built himself. Jupiter is more massive than everything else orbiting the Sun added together by a factor of about 2.5, and it is nowhere near being a star. The gap is larger than it looks. Its mass is 318 times Earth's. It exceeds the combined mass of all the other planets, moons, asteroids, and comets in the solar system. That has consequences for the geometry. The Sun and Jupiter orbit a common center of mass that sits just outside the Sun's own surface, which means the Sun is genuinely moving in a small circle rather than sitting still. To ignite fusion, though, Jupiter would need to be about 80 times more massive than it is. So it is the largest thing in the solar system that is not the Sun, and it is not remotely close to being a second one. The Great Red Spot has neighbors, and the Hubble Space Telescope has photographed 2 more red spots sitting alongside it. Storms on Jupiter merge and reform. The pattern of the atmosphere is bands. Alternating light zones and dark belts run parallel to the equator, driven by that extremely fast rotation. Within them, the vortices persist for years or centuries. Hubble has imaged 2 additional red spots adjacent to the Great One. The composition of the red material is still uncertain, though photodissociated ammonia reacting with acetylene is a likely explanation, and that is a chemistry nobody can sample directly. The storm is visible from Earth in a telescope with an aperture of 12 centimeters or more, which is a very ordinary instrument. Anybody with a modest telescope can watch the largest storm in the solar system from a garden. Nowhere on Jupiter does the atmosphere end and the ground begin, so the number everybody quotes as its radius is a decision rather than a measurement. The convention is a pressure level. Going down, the gas gets denser continuously. There is no phase change to mark a boundary, just hydrogen becoming steadily less like gas and more like liquid, then eventually like metal. So the surface is defined by agreement. The quoted radius is the altitude at which pressure equals 1 bar, which is the pressure at sea level on Earth, chosen because it is familiar rather than because anything happens there. A probe descending into Jupiter would never land. It would be crushed while still falling. The Galileo atmospheric probe managed 57 minutes and reached about 22 bars before it stopped transmitting. The stripes across Jupiter were noticed within 30 years of the telescope being invented, and the Great Red Spot may have been seen in the same century. Then it apparently vanished for 150 years. And so Fontana found the bands in 1639. Observers in the 1660s recorded a spot, and Giovanni Cassini, in particular, made careful drawings of a feature at the right latitude. The problem is what happened afterwards. Records of the spot become unreliable and then stop, and there is a long gap before the definite observations resume in 1831. Either the storm faded and reformed in nearly the same place, or the earlier sightings were a different feature altogether, or the observations were simply lost. Nobody can settle the question now, because the drawings that survive are simply not good enough to compare. There is a hexagon at the North Pole of Saturn with sides longer than the diameter of Earth, and it has been sitting there since we first looked. Nothing else out there has corners, not one thing. A persisting hexagonal wave pattern around the North Polar Vortex at about 78 degrees north was first noticed in the Voyager images, and each one of its 6 straight sides is roughly 14,500 kilometers long, which is a good deal longer than the entire diameter of Earth. The whole structure rotates once every 10 hours, 39 minutes, and 24 seconds. That is the same period as the planet's radio emissions, and therefore assumed to be the rotation of the interior. It also does not drift. Every other cloud feature in the visible atmosphere moves in longitude, and the hexagon stays put. Most scientists think it is a standing wave. Polygonal shapes have been reproduced in the laboratory by spinning fluids at different rates. The south pole of the same planet has no hexagon at all, which is one of the reasons the standing wave explanation is still only an explanation. Saturn is the least dense planet we know of, and it is less dense than water, which is a fact usually stated as a joke about a very large bathtub. The number is real, and it is worth looking up. Its mean density is 0.687 grams per cubic centimeter, measured against water at 1, which means that the average Saturnian material would indeed float if you could find an ocean anywhere large enough to test the claim properly. The average is doing a lot of work in that sentence, though. Most of Saturn's mass is nothing like the average, because hydrogen stops behaving as an ideal gas above about 1/100th of a gram per cubic centimeter, and the interior is far denser than the figure suggests. Pressure, temperature, and density all rise steadily inward until hydrogen becomes a metal. The planet as a whole would float in a sufficiently large ocean, and almost none of the actual material inside it would. Saturn is the one world where the length of the day is genuinely uncertain, and the reason is that there is no solid surface to time, and the magnetic field is too neatly aligned to help. Visible features rotate at different rates by latitude, so astronomers use three systems exactly as they do at Jupiter. System 1 at 10 hours 14 minutes for the equatorial region, System 2 at 10 hours 38 minutes for most other latitudes, and System 3 at 10 hours 39 minutes based on radio emissions. System 3 is meant to represent the interior, and that is the one everybody wants. The trouble is the method. At Jupiter, the magnetic field is tilted relative to the spin axis. It sweeps round, and the radio period gives you the interior rotation directly. Saturn's field is almost perfectly aligned with its spin axis, so there is nothing to sweep, and the trick does not work. Saturn has 293 known moons, only 63 of which have names, and one of them accounts for more than 90% of everything orbiting the planet. The rest is rubble, and most of it is very small rubble indeed. Titan alone comprises over 90% of the mass in orbit around Saturn, including the entire ring system. Everything else put together is a rounding error. Most of the others are very small indeed. 143 of them are less than 50 kilometers across. There is also evidence of dozens to hundreds of moonlets in the rings themselves, between 40 and 500 meters across, which are not counted as moons at all. Traditionally, they are named after the Titans of Greek mythology. The supply of names ran out long before the supply of moons did. Rhea, the second largest, may have a tenuous ring system of its own. Titan is the only moon anywhere with a proper atmosphere, and it is the only place besides Earth with standing liquid on its surface. The liquid is not water. It is not close. The atmosphere is thick enough that the surface pressure is higher than Earth's, and it is nitrogen-dominated with a complex organic chemistry running in it. It is the only satellite anywhere with weather in the ordinary sense. The lakes are hydrocarbons, methane, and ethane, liquid because the surface sits at about -179 degrees Celsius, filling basins near the poles and fed by rainfall from the clouds above. On June 6, 2013, scientists at a Spanish research institute reported detecting polycyclic aromatic hydrocarbons in the upper atmosphere, which are a possible precursor to more complex chemistry. So there is a moon with rivers, lakes, rain and seasons, running entirely on the wrong liquid. Saturn's rings are falling into the planet, and the measured rate suggests they will be gone in something like 100 million years. We happen to be here while they exist, and material at the inner edge is continually pulled down by gravity and by the planet's own magnetic field, which drags charged ice particles steadily inward until they rain down into the upper atmosphere and are gone for good. Cassini measured the infall directly. The figures imply a lifetime far shorter than the age of the solar system, which is itself an argument that the rings must be young. There's also a viewing coincidence. The rings are tilted, so from Earth they open and close over a 15-year cycle, and roughly every 15 years they present edge-on and effectively vanish. A disk 20 meters thick seen exactly edge-on from a distance of 1 billion kilometers is not visible at all. Galileo saw the rings in 1610 and had no idea what they were, and the description he settled on was that Saturn had ears. 2 years later, they disappeared entirely. So his telescope resolved something on either side of the planet, but never the shape of it, and he therefore reported Saturn as a triple body, with 2 smaller companions attached to a larger central one. Then in 1612, the rings turned edge on and vanished from view, which was baffling. He wrote about having been deceived. Christian Huygens worked out in 1655 that the planet was surrounded by a solid ring, and it then took a further 2 centuries before James Clerk Maxwell demonstrated mathematically that a solid ring could not possibly survive, and that it had to be countless separate particles instead. The answer arrived by proof rather than observation. Saturn was the outermost thing anybody knew about for the whole of recorded history until 1781, which meant it marked the edge of the universe for several thousand years. The names it collected reflect that. Babylonian astronomers observed and recorded its movements systematically, and in ancient Greek, it was Phanon. In Roman times, it was called the Star of Saturn, and also, curiously, the Star of the Sun. The Romans equated Saturnus with the Greek Cronus, and in modern Greek, the planet is still Kronos. Ptolemy based his calculations of the orbit on observations made at opposition. In Hindu astrology, it is Shani, one of the 9 Navagrahas, and Shani is the one who judges everyone according to their deeds, which is a reasonable role for the slowest and most distant thing anybody could see. Being the slowest visible planet, it became the one associated with time, age, and limits. Saturn was assumed to be a smaller copy of Jupiter, and its own gravity field says otherwise. It is far more concentrated toward the middle than it should be. Standard planetary models start from the assumption that the composition is broadly the same. A small rocky core wrapped in hydrogen and helium with traces of volatiles. But the gravitational harmonics and the oblateness disagree. Both indicate Saturn is significantly more centrally condensed than Jupiter, with a much higher concentration of heavy elements deep inside. The central regions are about 50% hydrogen by mass, where Jupiter's are closer to pure hydrogen and helium. The consequence is that most of Saturn's mass is not gas at all. Above a certain density, hydrogen stops being an ideal gas, and that threshold is crossed at a radius enclosing 99.9% of the planet's mass. Saturn's clouds are sorted into layers by what freezes at what depth, so the planet is banded vertically as well as horizontally. Only the top layer is visible. So in the upper cloud deck, at temperatures between 100 and 160 Kelvin and pressures of half a bar to 2 bars, the clouds are ammonia ice. Below that layer, the water ice clouds begin at around 2.5 bars of pressure and continue down to 9.5 bars, where the temperatures run from 185 Kelvin at the top of the range to 270 at the bottom of it. Intermixed in that layer is a band of ammonium hydrosulfide ice, sitting between 3 and 6 bars. The banding across the visible face is the same arrangement as Jupiter's and uses the same naming, but Saturn's bands are much fainter and much wider near the equator. Nobody saw the finer cloud patterns at all until the Voyager spacecraft flew past in the 1980s. Uranus appears in a star catalog compiled in 128 BC, listed as one of 4 stars forming a shape in Virgo, and one of those 4 stars does not exist. Uranus was standing exactly where it should have been. Hipparchus measured stellar positions in 128 BC for a catalog later folded into Ptolemy's Almagest, and the catalog records a quadrilateral of 4 stars in Virgo, of which only 3 can be found in the sky today. In April of 128 BC, Uranus was at the position of the missing one. It was seen repeatedly afterwards and never recognized. John Flamsteed observed it at least 6 times in 1690 and cataloged it as 34 Tauri. James Bradley saw it 3 times. Tobias Mayer saw it once in 1756, and Pierre-Charles Lemonnier observed it at least 12 times. without ever noticing that the thing was moving. A planet hid in plain sight for 18 centuries, sitting in the records under a different name the whole time. Uranus rotates on an axis tipped almost exactly into the plane of its own orbit, so it rolls rather than spins. Whether that counts as backwards depends on which convention you use. The tilt can be described as 82.23 degrees or as 97.77. The difference is not a disagreement about the measurement, but about which pole you decide to call north. Follow the International Astronomical Union definition, and the tilt is 82 degrees, and Uranus rotates retrograde. Follow the right-hand rule instead, and the tilt is 98 degrees, and the rotation is prograde. Both descriptions are correct, and the planet itself is entirely indifferent to which convention anybody chooses to apply to it. The practical consequence is severe seasons. Each pole spends 42 years in continuous sunlight and then 42 years in complete darkness. And at the solstices, one pole points nearly straight at the sun, while the other faces empty space. The lowest temperature ever recorded on any world at all was measured in the atmosphere of Uranus. And Uranus is not the furthest planet from the sun. Neptune is colder by distance and warmer in fact. The tropopause of Uranus has been recorded at 49 Kelvin, which is minus 224 degrees Celsius. That is the coldest measurement taken anywhere. But the reason it wins is that Uranus is barely producing any heat of its own. Its total heat flux is 0.042 watts per square meter, which is lower than Earth's own internal flux of about 0.075. A gas giant leaking less heat than a rocky planet, a 20th of its size. Neptune, its near twin in size and composition, radiates 2.61 times as much energy as it receives from the Sun. And Uranus radiates almost no excess at all. Uranus and Neptune are nearly the same size and made of nearly the same material, and one of them is pouring out internal heat while the other is not. The explanation is still missing. Neptune radiates 2.61 times the energy it absorbs from sunlight, which means most of its warmth comes from inside. Uranus radiates 1.06 times, which is essentially nothing. That is not a small discrepancy between twins. It is the difference between a planet that is still cooling and one that has apparently stopped. The leading suggestion is a giant impact early on, the same event that may have knocked the axis over, which could have disrupted the internal structure enough to trap heat or to have let it escape all at once. Why the internal temperature of Uranus is so low is still not understood. Nobody has a mechanism. The magnetic field of Uranus is not centered on the planet and is not aligned with its spin, and nobody expected either of those things. It is offset by 1/3 of the planet's radius. Before Voyager 2 arrived in 1986, there were no measurements at all, and the reasonable expectation was that the field would line up with the poles, which lie in the plane of the ecliptic because of the tilt. What Voyager found was stranger. The field is tilted 59 degrees from the rotation axis, and the dipole is displaced away from the middle of the planet toward the south rotational pole by as much as 1/3 of the planetary radius. So the magnetosphere is wildly asymmetric, and surface field strength differs enormously depending on where you measure it. Neptune turned out to have the same problem, which suggests the cause is in how these planets generate fields, rather than in the tilt. When Voyager 2 flew past Uranus in 1986, it photographed a featureless pale disk, and for years afterwards, the planet was described as dynamically dead. It was simply the wrong decade to look. The visible southern hemisphere divided itself into a bright polar cap and dark equatorial bands, with the boundary sitting at about 45 degrees south, and a narrow brighter band called the southern collar running just below that. Voyager saw 10 small bright clouds scattered a few degrees north of that collar, and essentially nothing else happening anywhere on the planet. And the timing explains it. Voyager arrived at the height of southern summer, with one pole pointed at the sun and the atmosphere in its least active state. Between March and May 2004, large clouds appeared, and observers recorded wind speeds of 820 kilometers per hour, along with a persistent thunderstorm somebody nicknamed the 4th of July fireworks. The dead planet had weather after all. Violent weather. The moons of Uranus are the only ones in the solar system not named from mythology, and the convention comes from two English writers. Somebody made a choice in the 1850s that stuck. All 29 known satellites take their names from characters in the works of William Shakespeare and Alexander Pope. The 5 main ones are Miranda, Ariel, Umbriel, Titania, and Oberon. Umbriel and Ariel are both from Pope's Rape of the Lock, rather than from a play. The system is also strangely lightweight. The combined mass of all 5 major satellites is less than half the mass of Triton alone, which is a single moon of Neptune. Titania, the largest of them, has a radius of only 788.9 kilometers, which is less than half that of our own moon. Uranus has 13 rings, and they are almost black, which is why nobody saw them until 1977. One observer claimed them in 1789 and was not believed, and the particles are extremely dark, ranging in size from micrometers up to a fraction of a meter, and 11 of the 13 rings are only a few kilometers wide. The brightest of the 13 is the Epsilon ring. Though brightest here is a strictly relative term when every particle in the system is nearly black. They are probably young. The dynamics indicate that they did not form along with a planet, and the material may once have been part of a moon or several moons shattered by high-speed impacts, with only those fragments sitting in stable zones surviving to the present day. William Herschel described a possible ring around Uranus in 1789, which was dismissed for nearly 2 centuries, and then turned out to be plausible. Uranus is the only planet of the 8 with a Greek name rather than a Roman one, and the man who discovered it wanted to call it something else entirely. The argument took 70 years to settle. Herschel proposed naming it after King George III, and for several decades afterwards, the English publications called it the Georgian planet, while the French ones simply called it Herschel, after the man himself. So the name that won came from Johann Bode. Uranus, the Greek deity of the sky, chosen because Saturn was the father of Jupiter, and Uranus was the father of Saturn, which continued the generational logic backwards. Caelus would have been the Roman equivalent. It would have matched every other planet in the sky. There is also the pronunciation problem. Astronomers prefer the stress on the first syllable, largely because the alternative sounds like something else, and both are formally acceptable. One orbit of Uranus takes 84 Earth years, which means nobody has ever watched it complete too. It has been a known planet for less than 3 of its own years. Herschel identified it in 1781, and 84 years later, in 1865, it returned to the same place in the sky for the first time since anybody knew what it was. By the time Voyager 2 arrived in 1986, it had gone round twice. The consequence for observation is awkward. Each season lasts 21 Earth years, so studying the seasonal behavior of the atmosphere requires a data set longer than most careers, and good atmospheric data only goes back a few decades. Determining the nature of that seasonal variation is difficult for precisely this reason. There has simply not been enough time to watch it happen. Uranus is bright enough to see without a telescope, and it was never recognized as a planet for thousands of years because it moves too slowly to notice. It hides by being patient. Its apparent magnitude sits between 5.4 and 6. That is within naked eye range for anyone under a properly dark sky who knows where to look. The problem is the motion. A planet is identified by moving against the fixed stars, and Uranus takes 84 years to complete a circuit. So from one night to the next, it barely shifts at all. Through a telescope, it shows a disk rather than a point, which is what finally gave it away to Herschel. Herschel himself initially thought he had found a comet rather than a planet. Uranus is called an ice giant, and there is very little ice in it in any ordinary sense. The word means something different in planetary science than it does in a freezer. The interior is thought to be a rocky core, a mantle of water, ammonia, and methane, and an outer envelope of hydrogen and helium. That mantle is where the term comes from. Astronomers call water, ammonia, and methane ices because they were solid at the time the planet formed, and inside Uranus today they are neither solid nor quite liquid, but a hot, dense fluid held under enormous pressure. Estimates put the temperature of that mantle in the thousands of Kelvin, which is a long way from anybody would recognize as ice. So the ice is hot. It is not frozen, and calling it ice is a statement about where it came from, rather than what it currently is. Neptune is the only planet that was discovered by working out where it had to be, and then pointing a telescope at that spot. It was found within a degree of the prediction on the first night of looking. Uranus was not behaving as it should. Its observed positions kept drifting steadily away from where Newtonian mechanics said they ought to be, and the residuals were far too large and far too persistent to be written off as measurement error by anybody who looked at them. Two people solved it independently. Urbain Le Verrier in France and John Couch Adams in England both calculated the position of an unseen planet whose gravity would account for the discrepancy. Le Verrier sent his figures to Johann Galle in Berlin. Galle found the planet on September 23, 1846, the very night he received the letter, less than 1 degree from the predicted position. A planet was located by arithmetic alone, sitting exactly where the arithmetic said it would be, before a single person had ever seen it through a lens. The credit was then argued over for a century and a half, bitterly. Galileo drew Neptune twice, in December 1612 and January 1613, and recorded it as a fixed star both times. He missed the discovery by a matter of a few weeks, through nothing worse than bad luck. His drawings from 28 December 1612 and 27 January 1613 contain plotted points matching exactly where Neptune was on those dates. It was close to Jupiter in the sky, which is why he was looking there at all. The timing was cruel. At the first observation, Neptune had turned retrograde that very day, so it was almost perfectly stationary against the background stars. A planet is recognized by the fact that it moves against the background stars, and Neptune, at that precise moment, was not moving at all. Had he looked a few weeks later, the motion would have been detectable in his own drawings, and the discovery would have come 233 years earlier. He's not credited with it, and the two sketches survive. The strongest winds ever measured on any planet are on Neptune, and it is the planet receiving the least sunlight of the 8. Nothing about that combination is straightforward. Wind speeds reach almost 600 meters per second. That is 2200 kilometers per hour, and faster than the speed of sound in Earth's own atmosphere at sea level. Most of those winds blow against the direction of the planet's rotation, which is unusual in itself, and the prevailing speeds at the cloud tops run from 400 meters per second along the equator down to about 250 at either of the poles. Neptune gets about 1,000th of the sunlight that Earth does, and weather is normally driven by solar heating. So on the face of it, there is almost none of the necessary energy available out there at all, and yet the winds are the fastest anywhere. So the energy has to be coming from inside. The pattern of prograde rotation at high latitudes against retrograde at low ones is thought to be a skin effect rather than anything deep. Neptune radiates more than 2.5 times as much energy as it receives from the Sun, which means most of its warmth is coming from somewhere inside it. Nobody knows what the source is, not even roughly. The figure is 2.61 times the absorbed solar energy, and that is a very large excess for a planet that formed 4.5 billion years ago and should have finished cooling. The comparison with Uranus makes it worse rather than better, because Uranus is nearly the same size and composition and radiates only 1.1 times what it absorbs from the sunlight reaching it. Neptune is over 50% further from the Sun than Uranus, receives roughly 40% as much sunlight, and yet its internal energy is enough to drive the most violent weather in the solar system. As with Uranus, the source of the heating is unknown. Voyager 2 photographed an enormous storm on Neptune in 1989, and when Hubble looked for it 5 years later, it had gone completely. A different storm of much the same kind had appeared somewhere else on the planet entirely. The Great Dark Spot was an anticyclonic system spanning 13,000 by 6,600 kilometers, which makes it roughly the width of the Earth, and it closely resembled the Great Red Spot on Jupiter in almost every respect, except that it did not last. On November 2, 1994, the Hubble Space Telescope found no trace of it anywhere on the planet, and instead, there was an entirely new storm of similar character sitting in the northern hemisphere. So Neptune's storms are not permanent features. They form, persist for a few years, and dissipate, which is the opposite of Jupiter's behavior, and nobody is certain why the two planets differ. Voyager also tracked a fast-moving white cloud group further south, which the team nicknamed the Scooter because it kept overtaking the dark spot. The largest moon of Neptune orbits backwards, which means it did not form there. It was captured, and it is now falling in. Triton accounts for more than 99.5% of the mass in orbit around Neptune. It is the only one of the 16 moons massive enough to have pulled itself into a sphere. Unlike every other large moon we know of, its orbit is retrograde, running against the direction of the planet's own rotation, and there's simply no way at all for a moon that formed in place around a planet to end up traveling backwards like that one does. So it was probably a dwarf planet in the Kuiper belt that came too close. It is now tidally locked and slowly spiraling inward, and in about 28 billion years it reaches the Roche limit and is torn apart into a ring of debris. William Lassell found it 17 days after the planet itself was discovered. In 1989, Triton was the coldest object anybody had ever measured, at 38 Kelvin, and its surface is partly nitrogen frost. It also has geysers, which is not what anybody expects from a surface that cold. That temperature is minus 235 degrees Celsius, cold enough that nitrogen freezes solid and lies across the ground as frost. Voyager 2 nevertheless photographed dark plumes rising several kilometers and being blown downwind. They are thought to be nitrogen geysers, driven by weak sunlight warming subsurface ice until it bursts through. Sunlight at 30 times Earth's distance from the Sun, which is about 1,000th of what falls on us, is apparently enough to do that. The surface is also remarkably young geologically, with very few impact craters, which means something has been resurfacing it in the relatively recent past. So there is a frozen moon out there, going the wrong way around its planet, and still geologically active after 4.5 billion years. Neptune's magnetic field is tilted 47 degrees from its rotation axis and offset from the middle of the planet by at least 13,500 kilometers. Uranus has the same problem, and that ruled out the obvious explanation. Before Voyager 2 reached Neptune, the assumption was that the peculiar Uranian field was caused by the sideways rotation, because a planet lying on its side might reasonably have a strange field. Then Neptune, which has an ordinary 28-degree tilt, turned out to be just as skewed. So the tilt is not the cause. Comparing the two fields now suggests that the extreme orientation is characteristic of how these planets generate their fields at all. Probably by convection in a thin spherical shell of electrically conducting liquid. Most likely some mixture of ammonia, methane, and water under pressure. The field is not being generated in a core at all, as Earth's is, but somewhere out in a thin shell of conducting fluid. Neptune has completed exactly one orbit since it was discovered, and it finished in 2011. 1 year there lasts 165 of ours. Gally found it in September 1846, and the planet returned to the same point in its orbit in July 2011, which is the only anniversary it has ever had. The seasons run to scale. Axial tilt is 28.32 degrees, similar to Earth's 23 and Mars's 25. So Neptune has ordinary seasons, and each one lasts about 40 Earth years. A single Neptunian summer, therefore, lasts longer than most human lives, and nobody has ever observed one from beginning to end. The day, by contrast, is short, about 16.11 hours, and because the planet is not solid, the wide equatorial zone takes 18 hours, while the poles take 12. Neptune has carved gaps into the region of space beyond it, and the objects that survive out there do so by keeping time with its orbit. Pluto is one of them. The Kuiper Belt is a ring of small icy worlds, much larger than the asteroid belt. It extends from Neptune's orbit at 30 astronomical units out to about 55. Neptune's gravity dominates it in the way Jupiter's dominates the asteroid belt. Over the age of the solar system, certain regions were destabilized entirely, leaving gaps behind. The band between 40 and 42 astronomical units is one example. Objects can survive inside those gaps, but only in resonance. Their orbital period has to be a precise fraction of Neptune's. Pluto sits in a 2 to 3 resonance, completing 2 orbits for every 3 of Neptune's, which is why the two never collide despite crossing paths. Neptune's rings are faint, dark, and gathered into arcs rather than spread evenly, which should not be possible for long. Something is holding the clumps together. There are 5 known rings, all made of very dark material, and the outermost of them, atoms, is the one that causes the trouble. Instead of forming a continuous band, it is bunched into distinct arcs, which have been given names: Liberté, Égalité, Fraternité, and Courage. The problem is that orbital mechanics should smear clumps like that into a uniform ring fairly quickly. They have not smeared in decades of watching. The likely answer is the small moon Galatea, whose gravity shepherds the loose material into place and holds it there, though the arcs themselves have also been observed to change substantially over the course of a few decades. One of the arcs, Liberté, has been observably fading over the past few decades. Exactly 1 spacecraft has ever visited Neptune in 1989, and there are no confirmed plans to return. Everything we know closely comes from a single flyby. Voyager 2 passed within about 4,800 kilometers of the North Pole on the 25 August 1989. It had taken 12 years to get there, and it left within hours. In that time, it found the Great Dark Spot, the Scooter, 6 new moons, the ring arcs, the offset magnetic field, and the nitrogen geysers on Triton, which is a remarkable return for a few hours of work. Then it carried on out of the solar system altogether, and nothing has been back to Neptune in the 30-odd years since. Every image of Neptune since has come from telescopes, which is why the pictures are all disk and no detail, and why storms come and go without anyone watching closely. The nearest thing to a plan for going back is a proposal, and proposals are not missions. Pluto was discovered in 1930 and has not yet completed a single orbit since. It has another 84 years to go before it gets back to where it started. One Pluto year is 248 Earth years, so the planet, or the dwarf planet, has traveled only about a third of the way around its own orbit since Clyde Tombaugh first found it on a photographic plate. Tombaugh was 24 years old and comparing photographic plates by hand, looking for something that had shifted position between one exposure and the next, while everything else stayed put. There was a longer coincidence in the timing. Pluto was near its perihelion, the closest point to the Sun in its very eccentric orbit, through the late 20th century, which is precisely when anybody had the instruments to look properly. It has been receding ever since, and will keep receding until 2114. Everything we know about it, we learned while it was as close as it gets. For 20 years out of every 248, Pluto is closer to the Sun than Neptune is, and the two can never collide. The arrangement is held in place by a resonance. Pluto's orbit is eccentric enough that it crosses inside Neptune's, and it spent the whole of the years from 1979 to 1999 being the 8th planet out from the Sun, rather than the 9th one. The reason they never meet is timing rather than luck. Pluto completes 2 orbits for every 3 that Neptune manages, which is a 2 to 3 resonance, and it means the two bodies are never in the same part of the solar system at the same moment. The orbit is also tilted 17 degrees out of the plane, the planets share. So even at its closest crossing, Pluto is a long way above or below where Neptune actually is. Pluto has mountains 3 kilometers high, and they cannot be made of the material covering the surface. At that temperature, nitrogen ice has the strength of toothpaste. The surface is largely nitrogen and methane ices at about 40 Kelvin, and neither is remotely strong enough to hold up a mountain range against its own weight. Water ice is different. At 40 Kelvin, water ice behaves very much like rock, which means the mountains New Horizons photographed in 2015 have to be water ice bedrock, with the softer ices lying over the top of them like snow. Some of them rise 3,500 meters. The same flyby found a plain with no impact craters at all, Sputnik Planitia, which means the surface there is being renewed by something. On a world that should have frozen solid billions of years ago, the bright region on Pluto that everybody recognizes is a glacier of nitrogen ice, and it is convecting. The surface is turning over in cells, like water in a pan. Sputnik Planitia forms the left lobe of the pale heart shape, and it sits in a basin roughly 1,000 kilometers across, filled to a depth of several kilometers with nitrogen ice. The polygonal patterns visible across it are the tops of convection cells. Warmer ice rises in the middle of each cell, and colder ice sinks at the edges of it, exactly as a heated fluid does, driven along by the faint trickle of heat still leaking out of Pluto's interior. Each cell is 10 to 40 kilometers wide, and the overturn takes perhaps 500,000 years, which is why there are no craters there. The surface keeps replacing itself. A glacier flowing on a world where the sun is a bright star. The Kuiper Belt contains hundreds of thousands of icy bodies over 100 kilometers across, and together they add up to a fraction of a percent of Earth's mass. Something took most of it away. The belt extends from Neptune's orbit at 30 astronomical units out to about 55, and it is far larger than the asteroid belt in both volume and population. But models of how it formed predict a great deal more material than is actually there, by a factor of somewhere between 100 and 1,000. The favored explanation involves the giant planets migrating early in the solar system's history, scattering most of the original population outward or inward and leaving a remnant. So what we see is not a belt that formed this way. It is the small proportion that survived. There is an object out there whose orbit takes it 937 times further from the Sun than Earth is, and nobody can account for how it got onto that path. It should not be possible. Sedna was found in 2003, and its orbit ranges from 76 astronomical units at its closest to about 937 at its furthest, taking roughly 11,400 years to complete. The problem is that closest point. At 76 astronomical units, Sedna never comes near enough to Neptune for Neptune's gravity to have flung it out there, which is the usual way objects end up on extreme orbits. Something else must have done it. Candidates include a passing star early in the solar system's history, or a body in the outer system nobody has found. Sedna is also one of the reddest objects known, nearly as red as Mars. The outer boundary of the solar system is a shell of comets that nobody has ever observed directly, and its existence is inferred entirely from the paths of objects that fall out of it. It may hold 1 trillion of them. The Oort cloud is thought to begin somewhere around 2,000 astronomical units and to extend out to perhaps 100,000 of them, which is a substantial fraction of the entire distance to the nearest star to our own. Nothing in it has ever been imaged in place. Every individual object is far too small, far too dark, and far too distant. What gives it away is the long-period comets. They arrive from every direction rather than from the plane that the planets share, and they come in on orbits so enormously long that they cannot possibly have originated anywhere nearby. John Oort worked the distribution out in 1950 from the statistics of comet orbits, an entire structure deduced from the things leaving it. 2 spacecraft have left the region of space controlled by the Sun, and both were built in the 1970s. Nothing else has managed it. The heliosphere is the volume of space where the solar wind dominates over the interstellar medium, and its outer boundary is the heliopause, which sits somewhere more than 50 astronomical units out from the Sun. Voyager 1 crossed on August 25, 2012, at approximately 122 astronomical units, which was recognized by a sharp rise in cosmic ray collisions and a sudden drop in the lower energy particles coming from the Sun. Voyager 2 followed in 2018. Both are still transmitting on plutonium power sources that are slowly fading from a distance where a radio signal takes about 22 hours each way. They will keep going for millions of years after the transmitters fall silent. Several distant objects have orbits that appear to be clustered in a way that random chance does not easily explain, and one proposed reason is a planet nobody has found. The argument has been running since 2016. The objects in question all sit beyond the Kuiper belt, and their orbits share an alignment both in the direction of closest approach and in the tilt, which is not at all what a randomly scattered population of objects ought to look like. One explanation is a large body further out, shepherding them gravitationally. The alternative is that the clustering is an artifact of how they were discovered. Surveys look at particular parts of the sky at particular times, and that can manufacture apparent patterns. But searches have not found anything. The proposed planet, if it exists, is very far out and very dark. Pluto and its largest moon are close enough in mass that they orbit a point in empty space between them, and both are tidally locked to that point. Neither one is really going around the other. Charon is about half Pluto's diameter and roughly 1/8 of its mass, which is by far the largest moon-to-planet ratio anywhere in the solar system. The barycenter, the common center of mass, sits outside Pluto's surface. So Pluto wobbles around a point in space rather than sitting still while Charon circles it. Both are locked. Charon always shows Pluto the same face, and Pluto always shows Charon the same face, and neither ever sees the other set. The other 4 moons are tiny. and 2 of them tumble chaotically. Pluto stopped being a planet in 2006 because of a definition written partly to exclude it, and the vote that settled it was taken by a fraction of the astronomers eligible. The reason was other discoveries. The trigger was Eris, found in 2005 and initially thought to be larger than Pluto, because if Pluto counted, then Eris had to count, and behind Eris were dozens more. The International Astronomical Union then adopted 3 criteria. It must orbit the Sun, it must be massive enough to be round, and it must have cleared its orbital neighborhood. Pluto fails the third. It shares its region with a great deal of other material. The vote itself was contentious, and the definition is still criticized, partly because clearing the neighborhood is a property of where an object is rather than what it is. Eris turned out to be slightly smaller after all. There is no agreed edge to the solar system, and the candidate answers differ from one another by a factor of about 1,000. It depends entirely on what you mean by edge. If the edge is where the planets stop, it is Neptune at 30 astronomical units. If it is where the Sun's magnetic influence ends, it is the heliopause at roughly 122, and Voyager 1 has already crossed it. If it is where the Sun's gravity stops dominating, it is the far side of the Oort cloud, somewhere around 100,000 astronomical units, which is nearly 2 light-years and about halfway to the next star. All 3 are used, in different contexts, by people who know exactly what they mean. The Sun keeps hold of things much further out than it keeps them lit. That is the 120. Some of them were facts, worked out and settled and checked. A fair number were not, and those are the ones still sitting open in somebody's notes tonight, waiting for an instrument that has not been built yet. If you are still awake, the rest of the solar system is on the channel, and there will be another one of these before long. And if you're not awake, then it worked, and none of this last part matters at all. Everything you have heard tonight was worked out by people who mostly never found out whether they were right. Sleep well.